given an object D in the three-dimensional space and a density function such that it assigns to each point of the object its density, so we can calculate what is the total mass of the object by just integrating the density over the object. So again, we are using the integral as a way to add. We are adding the density at each point of the object. So, for instance, to calculate the mass of an object D whose density is 3, I mean in all the points is uniformly dense, in all the points of the object the density is equal to 3. And this object is bounded below by the plane z equals 0. So if we have our system of coordinates here, the plane z equals 0 will be the plane of the floor, of the ground. And above is bounded by the surface z equals 4 minus x squared minus y squared. So this is a surface that the intersection here will be when x is 0 and y is 0, we have that z is 4, and when z is 0, we have here a circle determined here. This will be 2 and 2. We have a circle here, and so our surface is something like this. So the space inside of this surface, I mean under the surface and above the ground, so this is the object whose density is equal to 3 at each point of it. In order to calculate the mass of the object, we just need to calculate then the triple integral over d of the density, that in this case the density is just a constant function equals to 3. Okay, so this is the integral that we need to calculate. So in order to find the extremes of evaluations of this solid, we can see that because of the shape of this solid, it would be more suitable to use cylindrical coordinates that we have studied before. So then to describe the solid using cylindrical coordinates, we have that the r here is going to vary between 0 and 2, right? So we have between 0 and we'll go all the way until 2, where the z variable is going to go from 0 also, I mean from this ground here, to the top that is given by this, which is 4 minus x squared plus y squared, but we know that x squared plus y squared is r squared, right, in cylindricals. And finally, the angle is going to vary all the way, right, from 0 to pi. Okay, so we can see that we have a very easy description of this solid if we use cylindrical coordinates. So then we are going to solve this integral by using this change of variables. This is going to be the integral, the triple integral, where inside we are going to put 3 times, and remember that in cylindrical coordinates you have to multiply by r. And so the variation of the z is going to be between 0 and 4 minus r squared. And the variation of r is going to be between 0 and 2. And finally, the variation of the angle is going to be between 0 and 2 pi. Okay, so once that we set up the integral, so we are going to have the numbers going outside of the integral. This is going to be 3 times the integral between 0 and 2 pi, and the integral between 0 and 2. Remember that first we need to do this integral. So we're going to have dr d theta but inside here we are now solving the integral of r dz. So r is a constant with respect to z, and so the integral is just z, and it's going to be evaluated between 0 and 4 minus r squared. Okay, so this is the integral that we will solve next, but before, let's actually do this evaluation. So when we evaluate z between these two, we are going to get here r times 4 minus r squared minus 0, so just 4 minus r squared. Okay, so then this is the integral that now we have to do between 0 and 2 dr. And then still keeping outside the integral between 0 and 2 pi d theta and the 3 that we have in front. Okay, so next thing will be to do this integral now respect to r. So let's do the multiplication here of these polynomials. So that will be here 4 times r, 4r minus r cubed. And so the primitive of this function now will be 3 integral 0 to pi, and now we are going to integrate directly this function. The integral of 4r will be 4r squared over 2 minus the integral of r cubed 4 over 4, and this is going to be evaluated between 0 and 2. Okay, so let's evaluate between 0 and 2. So here 4 over 2, we just can put 2 there, and so when we evaluate at 2, that will be equals to 3 times the integral between 0 and 2 pi and now we are going to evaluate at 2. So we're going to have here 2 times 2 squared, which is 4, minus 2 to the 4th power, which is 16, over 4, which is 4. And so this is just a number, right? So here we have just 8 minus 4, so it's just the integral of 4 there, that we can take it out, multiply by this 3, 4 times 3 will be 12, and the primitive of this is just theta evaluated between 0 and 2 pi. And so the final result will be 12 times 2 pi, which is 24 pi. Okay, so we add then all the densities and we obtain then the mass of the object. The mass of the object will be 24 times 3.14. We're going to define what are called the moments with respect to the axis. The object is going to have 3 moments, and these moments are going to be useful in order to calculate the center of mass of the object. So the definition of the moment xy is going to be the integral of the density multiplied by the other variable. So if we are talking about the plane determined by x and y, so we are going to put z in the multiplication of the integral. And in the same way, we are going to calculate the xz is going to be the triple integral where we put y times the density. And the yz is going to be the triple integral where we put the other one, that in this case will be x times the density. So this will be the way to calculate the moments, and then the center of mass is a point in the object that we're going to call it x bar, y bar, z bar, and these numbers are going to be calculated by each moment divided by the mass that we just calculate. So for instance, the x component of the center of mass is going to be calculated as the moment yz, I mean the other 2 variables, right, divided the mass. And so the bar y is going to be mxz divided by the mass, etc. So for instance, let's calculate the center of mass of this object that we know already what the mass is, right? So we know already all the all the denominators. So let's calculate now what are the moments. Let's calculate just one of them first. So let's see, let's calculate mxy. So that will be the triple integral where we put inside z times the density, right? That in this case the density was 3. And we know already that for this domain is going to be beta the cylindrical components, so we are going to introduce here the r dz dr dz. So we know that in the change of variables, so z is equal z, right, in the case of cylindrical components. Okay, and so we put the correct variations here, so that will be here the integral. We know already these variations we did before, right? 0 to pi, 0 to, and we can put the next one that is 0 4 minus r squared, and so here inside is going to be 3rz dz. Okay, so let's do the integrations here. We're going to do just this integral now. So the here is going to be dz, so 3r is going to be a constant, 3r could be outside, and we're going to integrate just z, that is going to be z squared over 2. And we're going to evaluate between 0 and 4 minus r squared. And so this will be dr d theta. Okay, so we are going to do this evaluation now, considering that the variable is z, right? So then this is going to be 3r over 2. That is not going to be affected by the evaluation. And we are going to evaluate here 4 minus, substituting z by 4 minus r squared. So we're going to get 4 minus r squared squared. And then we're going to have dr d theta. Okay, so now the next integral to do now is this integral with respect to r. Let's expand this square, so that will be 16 minus 8r squared plus r to the 4, and this multiplied by cr, 3r over 2. So let's do these operations. And now this is the function that we need to integrate. So that will be 0 to pi, and so the integral of this one will be the 3/2, we leave it out, and the integral of this will be 16 r squared over 2 so the evaluation here will be 3/2 times 8 times 4 minus 32 plus 32 over 3. Let's simplify, and this is 32 minus 32 is 0, so we have just 32 thirds times this, the 3 cancel, and 32 over 2 is 16. So at the end of the day, we have just the integral here of 16. Which will be then 16 times 2. Okay, so this is going to be then the momentum with respect to the xy plane. The momentum with respect to yz, so then will be again the triple integral. We know already the extremes of variation here, but now we're going to write, since I put here yz, we are going to put here x, the variable that remains. But remember that x in the change of variables in cylindricals is not like the z that is equal to z, but the x is equal r cosine theta. So that's what we're going to write here. So here will be r cosine theta. And then we're going to put the density, and then we're going to put the r that is needed in the cylindrical change. And then dz, dr, and d theta. Observe that this is all a constant respect to z, so then we're going to have here 3r squared cosine theta, and so z evaluate between 0 and 4 minus r squared. So when we do this evaluation, we end up having the integral between 0 and 2, right? This integral here of, and when we do the evaluation, we get here r squared cosine 4 minus r squared dr. And then the integral between 0 and pi dz. Okay, so in order to integrate this, now the cosine, we have a 3 also there, the cosine is also a constant together with the 3, so they can all go out of the integral, and so we are going to get the 4r cubed over 3 minus r5 over 5. And this should be evaluated between 0 and 2, and we have outside the cosine, and we have outside also the 3. And this will be evaluated between 0 and 2 pi. So when we evaluate this function between 0 and 2, we will get a number, and we have a number here, and we have cosine here. So considering all this, you can do these operations, and you will see that you will get just a number that you can put outside, multiplied by the integral of cosine, but the integral of cosine is sine, and so as soon as we evaluate this between 0 and 2 pi, we are going to get a 0 no matter what the number we obtain in this evaluation. Well, in the same way, you can also check that m, when we do here the xz, for the same reasons, you're going to get a 0 too. And so the center of mass of this object is going to be then 0, 0, and 32 pi divided by the mass. Remember that we calculated the mass before. And so the center of mass is going to be 0, 0. Simplifying here, we will get 4/3. So that's the result then of the center of mass of the object.